Imagine designing a modern mega stadium. You must know exactly how tens of thousands of people will navigate to the exits in an emergency. You cannot wait until opening day to find out if your design works. Discovering a flaw during an actual crisis is a risk no architect is willing to take. Instead, engineers build the stadium inside a computer first. They run a digital evacuation before a single brick is even laid. But a digital test is only a prediction. If we are going to trust a computer's math with human lives, we need a way to prove that the prediction is actually right. Scientists test these designs by dropping thousands of tiny digital humans into a 3D blueprint of the stadium. These dots follow a few basic rules. Find the nearest door, walk toward it, and stay within the walls. When you hit play, the simulation runs smoothly, and the entire digital crowd makes it outside in exactly 5 minutes. But these dots are following lines of code, not human instincts. How do we know they behave anything like real stressed people? Proving the digital world matches our own requires a process called validation. It's the scientific standard for making sure a model is actually fit for its purpose. Validation is the necessary hurdle we cross to turn a neat computer simulation into a reliable, life-saving tool. Because human behavior is so varied, there is no single magic test. Instead, scientists use a layered toolkit, starting with something very simple, just watching. Researchers watch the simulation play out frame by frame to spot obvious errors that raw numbers might hide. For instance, you might see your digital people walking directly through a solid concrete wall like ghosts. Once researchers correct the code, the wall becomes solid and the dots pool and redirect toward the proper exit. This visual check ensures the basic rules of physics and geography are working before moving on to more complex questions. The next tool is a reality check. Engineers take the computer's results and put them side by side with records from actual events. They find a real stadium of a similar size and pull the security footage of a crowd emptying out after a game. This chart compares that real footage to the computer's guess. The line on the left shows the real crowd getting out in 15 minutes. The line on the right shows the simulated crowd still inside after 2 hours. That gap proves that the rules inside the computer are out of sync with reality. This keeps the digital model grounded in documented human behavior, rather than just theories. Next, the team has to poke and prod the model to see where it breaks. They want to know how the whole system reacts if they change the starting conditions by just a tiny amount. Imagine taking the simulation and increasing the crowd size by only 5%. If that small addition causes exit times to jump from 10 minutes to 10 hours, the model is too fragile to trust with a real design. Scientists also dig into the raw data to find hidden patterns. This graph shows the random numbers a computer used. While the points look scattered, the analysis in panel B shows they actually fall into rigid, artificial lines. Finding these glitches ensures the model works because the logic is sound, not because the conditions were perfect. Even with the best data, humans are messy. In a crisis, we don't always follow the shortest path or the most logical plan. To capture that human element, researchers run physical drills in warehouses with fake walls, asking real people to find their way out. They track every unpredictable, split-second decision those people make while navigating the space. Then they compare those messy human choices to the digital agent's choices in the same layout. When the digital dots start mirroring those real human reactions, it's a major step toward building a model that can reliably guide safety decisions. Validating a simulation isn't about checking a single box. It's a strategic combination of all these different tools. The situation dictates the approach, using historical records when they exist, and physical drills when the situation is brand new. At its heart, a computer simulation is only as useful as the trust we can prove it has earned. All those digital tests exist for a single reason: to make sure the physical world you walk through every day is as safe as possible. By putting our digital models through these tests, we can move from guessing how a crowd will move to knowing they'll get home safely.